Hey everybody, it's Brandon from STEM Tutor Club, and today we're going to talk about why this exponent property makes sense. This is usually called the power rule, and we're going to first get into some examples and then explain why this is always true. So to start off, let's actually work through an example with actual numbers just to see how it behaves. Now there are two ways to do this. One is the normal way without using the property, and the other is to use the property. So we're going to start just calculating this expression, 2 squared cubed, the way we normally would if we didn't know about this way to simplify it. So if we work this out, 2 squared, that would be 2 times 2, which would be 4. And then that 4 will be left inside of the parentheses, and then it will be cubed. 4 cubed is 4 times 4 times 4, which is 4 times 4 is 16, and then times 4 again would be 64. So that's the way we would calculate it normally. However, if we were looking at it through this new perspective, we would say that m, which is really our internal exponent, that would be 2. And then we would say that n, our external exponent, would be 3. And then we would say that our base here is also 2. And if we use these values, then you can see that we would, on the left side, we would have 2 raised to the second power cubed. And according to this formula up top here, the right side of that equation, we would just use the same variables for, or the same values for x, m, and n, but we would be able to arrange it in this new form. Basically, we'd be able to just multiply the exponents. So if we did that, we would get 2 raised to the power 2 times 3. And if we simplify this entire thing, 2 times 3 would be 6, so this would be simplified to 2 to the 6th power. And if you actually calculate this on a calculator, you'll find that this actually also equals 64, as we expect. So this is sort of two ways of calculating this expression. It's basically doing an exponent one after the other. So one exponent inside of another exponent. And we can do it without the property, but if we use the property, we can, in some cases, calculate it more quickly. Now, I just want to make a quick note on why this is useful, because it might seem like just doing what we did on the left-hand side is actually easier, and in some cases that is true. In most cases, I would say it's actually true if you know all the numbers. Where this would really be useful is in cases where you don't know, for example, the base. So if we represent the base with just an x, which again represents an unknown, so we don't know what x is equal, well, there's no real way to simplify this expression outside of using this property. So if we use this property, then the way we could represent it is we might not know what the base is, so we have to leave that as an unknown x. But we do know that we can simplify the exponent by doing 2 times 3, which is 6, and we can represent it here. And here you see that x to the 6th power is simpler conceptually than x squared and then the whole thing cubed. So that's where this property really comes in handy in an algebra class. Now I want to explain exactly why it works. So here, as with all exponent properties, the best way to understand why this works is to just use the definition of exponents to expand out the entire expression. So for example, 2 squared, what does that mean? Well, it means 2 times itself twice. So we would represent that as parentheses 2 times 2. And then what does cubed mean? Well, it means that we need to take, in this case, everything inside the parentheses. So we're cubing the entire expression inside the parentheses. So whatever is inside of that, we need to multiply it by itself 3 times. So we would have 2 times 2 in parentheses times 2 times 2 in parentheses. So now we have 2 sets of parentheses. And if we're cubing, then we need a third one. And then based on the associative property, you can basically drop the exponent or drop the parentheses. And you can see here, you can actually count them out. 1, 2, 3, 4, 5, 6. You can see that we have 2 multiplied by itself 6 times, which is by definition 2 to the 6th power. So that's a quick example of how it works in a specific case. The basic idea is that whatever the external exponent is, that's how many sets of parentheses that you will have. And inside each set of parentheses, the amount of your base that you will have multiplied together is the internal exponent. So hopefully that makes sense for why we would end up multiplying them. Here it's because we have basically 3 sets of 2 2's. So 3 sets with two 2's each in them. Hopefully that's clear why that would give us 6 2's. And this logic applies to anything, no matter what these numbers are. And I'm going to give an example of that in the next section. So here I'm going to try to prove the property a little bit more abstractly than what we've done before, or just to give you mostly an intuitive idea of why it's still true no matter what m and n is. And the basic idea, the basic way that we're going to work this out is we know that x to the mth power is going to be x times x times x times, however many x's there are. We don't know, but we're going to represent that as basically having m times. So x multiplied by itself m times is the definition of x to the mth power. And then we're going to have a number of these sets. We're going to have n sets like this. So I'm just going to write 2 of these, but these dots in the middle mean that there's a lot more. So if we write this out, just to finish this off, this would also be, m x's. So I'll say m times down here. And in terms of the total number of sets that we have, so this would be like one set, and there might be another set here, dot, dot, dot. We don't know. We don't actually know how many sets there are. We just know that there are abstractly n. So what we would say is that there's a total of n sets. N sets. And then if you think about it here, hopefully it's clear that if we have n sets, and each set has m x's in it, then we should end up with m times n x's. So that's a little bit more abstract, but that's the general idea. So I hope this video made this specific exponent property make more sense. Be sure to stick around for the next one where we go over the next exponent property in our series, the product of powers. See you then.